MIT has an educational philosophy of learning by doing. So it's fine to know about the theoretical equations. It's quite another thing when you actually have to build something. And for a lot of students, this is the first time they've ever built anything. If you take RTV, it's kind of a rubber. So Capstone class, it's where you take the different things you've learned in your undergraduate education and pull them into something that integrates them. In our case, we do a capstone class looking at the design and construction of either an airplane or a spacecraft.
There's a lot of systems that have gotten a lot of recognition that started with a senior capstone class. So it would always be awesome to be the next iteration of that.
3, 2, 1, and we're flying.
These innovative solutions that students come up with into this challenging problem. That's what's really unique, and that's what us persons really value.
How do we connect to?
You don't really build much in the first semester, and you're not meant to. The idea is for everyone to come in to work with their models, to come up with ideas and sketches, and then in the spring you take the old designs and you iterate on them experimentally, and then you build them and you try to get the thing to fly.
We wanted to create an unmanned aerial vehicle along with a submersible system that will be used to either conduct reconnaissance or search and rescue missions in blue water operations.
The project was sponsored by the Office of Naval Research, and the motivation was to be able to resupply a UAV in deep water when you're away from land.
When I first heard of it, I was like, oh wow, this is so cool.
One of the major problems with seaplanes is that they can dig their pontoons in and flip upon landing.
The students came up with a relatively ingenious idea of having the pontoons rotate so that if the airplane did end up on its back, it wouldn't be like a turtle on its back, it would be able to get flipped over.
There's a worm gear system inside the airplane that tilts the pontoons, so it kind of does an upside down push-up. Then the body actually is lifted out of the water, and then the body is then free to rotate around.
There's a very strong software and autonomy component. So the pod knows where it is with its local GPS system. So it broadcasts a message to the airplane, I'm at this location. The airplane comes and lands close to that location. They use an optical camera that was sensitive to certain colors. They put colored markers on the pod so that the optical system would know to look for the signature of the pod. Now that sounds pretty easy, but it actually gets tough because now you're in rough water. So the pod isn't still, it's going up and down. The airplane's being bounced around, so it has to find that target, and it has to sort of average out where the target's going to be and head in that direction. As it gets closer and closer, it gets a better and better fix.
Is someone recording the settings? Yeah, okay, do it. Ready? All right, ready? All right, full power, flat. Pontoons are submarining at speed, and I don't have enough Q on the tail to be able to bring the nose up. Yeah.
We couldn't get the airplane to take off. We tried a couple of different angles and flap settings and couldn't get it to take off. Diagnosed it as the pontoons submarining down into the water. Did a quick fix for that. Just mix up some glue and pieces of plywood to try to get the pontoons to sit up a little better.
Take off attempt 2.2.
You take it to the field and you try it. And if it doesn't work, you take video and you take measurements and you use that to refine your design.
First flight test, first crash, it's sort of the way it goes in this business.
Okay, let me try it. It's got a little too much here. Start with it.
We didn't actually get to fly, but we did learn what we need to be able to fly. Basically, we hadn't done enough surface area attachment on the inside of the carbon fiber, so the legs actually sheared, and we weren't able to take off properly on the final takeoff attempt. And then before that, we realized that our tail needed to be a little bit bigger so that we could have more nose control, nose authority. And then those are some of the modifications that we made so far, and hopefully it'll fly on Wednesday.
Awesome.
They're figuring out how things that look good on paper, theoretical models, work in the real world. They're understanding that you have to make approximations. You have to use engineering judgment. You have to decide what's important and what's not important.
Oh no, they glued it in wrong.
After the flight test at the pond, we made a bunch of changes to the aircraft. First of all, the biggest change is that we took the tail, which was here, which was too small, gave it a bigger tail, and put it here in the prop wash of the motors. And we included these scoops at the front of the pontoons to help with the pitch stability and the submarining problem on the water. And all these design changes have been carried over onto the new aircraft, which has these hooks here to allow the water to separate and for it to build up high pressure that keeps the pontoons from nosediving into the water. And this one has also been given a molded Kevlar fuselage to improve the aerodynamics and keep everything inside.
What's special about the capstone process is the fact that it's really simulating the engineering environment.
Many of the students describe their experience as transformational. They become fearless.
Automatic. Everybody is automatic mode now.
It's automatic.
The fact that they get to experience being both an engineer and a technician, somebody who actually is the one who puts these things together, I think makes them better engineers because they can learn to understand how their designs could actually be built.